morning, you know. Is it okay? I like the jobs. I like dinner. So they're probably gone on Friday. We did this fundraiser, like for the BCM, where they had like a beard auction, and so people were able to auction off their beers. And so the person that bid for this is what they chose. It was a lot of fun.
Who made the most money?
It was a student doing just she paid $110. Yeah. But other people, like one guy, Zach, I don't know if that's his last name, but he's an education major. He had a big old beard. His was like 120 or 125, and they just sort of took it down to like this big thing. Yeah. Because he had a really long beard. It was down to here, you know. And so they took off everything except for this. What's that?
That's depressing. That's a lot of work.
Yeah, yeah. And another guy, they didn't just do beards, they did hair too. The director of their concert, Sheridan, he had long hair and a long beard. He said, I'm not taking my beard off, so they took his hair off. And then another guy had really long hair. He paid, or a lady in the audience paid $200 to keep the hair. But then later it came out that he had actually just given her a bunch of cash and said that he didn't want anything. Anyway, it was a lot of fun. They raised $1,500 or so.
Did your kids freak out?
Yeah, my boy liked it. My girl said that she misses my beard because she knows it's coming off soon. Hey. Huh? Yeah, I'll probably grow it back for the fall. But let's see. Just sort of give you a heads up where we're headed. Friday is sort of our last class day. We'll sort of see where we go. We might actually not have class on Friday. Don't take that as a promise. It might happen, might not. But then Monday we'll have a review for the exam. No, Monday is the exam. Is that right? No, not this coming Monday. I mean the following Monday. I'm talking about not this Friday, but the next Friday. And then that following Monday is the exam, right? And then we have Wednesday, and we'll sort of come in and we'll go over sort of the format for the final. But y'all likely know the format for the final. But also, we can use that as a review session. No, we will have another review session later before the final. Is everything okay? Oh, don't worry about it.
He's like, hey.
You kind of look like exactly.
Yep, that's the point. Yeah, I went to see my first graders yesterday, and all the little boys were like, Wolverine!
You should spike your hair up.
Right, yeah. Alright, so far all we've looked at is Faraday's law, Lenz's law. Remember, Faraday's law is this idea that the EMF in an inductor is equal to L times, not d phi dt, the I dt. This isn't Faraday's law, but this is the EMF that's caused by an inductor, and we have seen also that the EMF is equal to, this is Faraday's law, the negative of the change in the flux with respect to time. We've had a couple problems like that where we have changing flux and we want to know the EMF that's induced by that changing flux. And we've also had this idea that the flux is equal to the integral of B dot dA. Right? We've seen flux before, but you'll see it again, and you had some homework probably at the calculate flux. So those are sort of our big ideas. We also have Lenz's law, which Lenz's law said that, this by the way is Faraday's law, but Lenz's law also says that the direction of the magnetic field opposes the changing of the flux. So the direction of the B field that's induced opposes the direction of the changing flux. And we saw several examples of that early on. But you had some in the homework on you had to apply resistance laws to determine the direction of the induced magnetic field. Remember, so if I have, say, a north pole going into a coil, then the opposing, or the magnetic field that's induced will be an opposing magnetic field. If it's coming away, that means a decreasing flux, and it's going to be in the same direction as. We had 4 different scenarios that we looked at. All right, we started looking at LC circuits, and we saw that LC circuits, you have this transfer of energy, right? The transfer of energy is from what to what in an LC circuit? That's right. So the electric field, the energy stored by the electric field is in which device? The inductor or the capacitor? So can you take me seriously? This looks like a trouble. So the electric field is stored in which device? The capacitor, right? Because you get those charges and they have an electric field in between them. And then the magnetic field is stored where? That magnetic energy is stored where? Right, in the inductor. And is the LC circuit, does it decay with time? Does the energy decay with time? No, time just transfers. Right, it just transfers back and forth. Because what type of forces are electric and magnetic forces? I haven't told you this, but you should know it. They're field forces, and field forces are what type of force? Big class of forces. Conservative, right? They conserve energy, so they never lose energy. They conserve energy. That means they're only due to these field forces, magnetic and electric forces, and so they always conserve energy, so they never lose energy. So in an ideal LC circuit, you're going to get this interplay of UL, or excuse me, UE and UV. Right, so when UV is small, UE is, or when UV is big, UE is small. The energy stored by the magnetic field is big, energy stored by the electric field is small, and then they'll switch back and forth, and they just oscillate. All right. So we saw that last time. Let's see, what was this? Oh, this was our LC circuit. Yeah, so if we're plotting out our UE, let's just do this here. Let's say that this is UE. When UE is at its maximum, UV is going to be 0. So if this is UV in the red, it's going to look like this. If I plot those two curves, when one is big, the other is 0. All right. Well, let's see. We're going to look at some circuits here. Let's look at this LC circuit. I have a capacitor with a 1.5 microfarad capacitor, and then I have an inductor. It's 12. Anybody remember the unit for inductance? Yeah, it's a Henry. So this is in millihenries. And the capacitor had previously been connected to a 12-volt battery. The cap had been charged by a 12-volt battery. All right, so we charge this capacitor, it stores energy, and then we can disconnect the battery, and that capacitor forever holds that charge. And then we hook it up to this inductor. All right, first question I want to know is what is the maximum current? You'll have similar questions in the homework. I'm not sure, I might have put one like that already, but if not, you'll have one today or tomorrow. What is the maximum current in this circuit? All right, so a couple ideas that we want to do. First of all, this thing doesn't lose energy. This circuit never loses energy because there are no resistors in it. And resistors are going to dissipate energy, but this one doesn't. So I have two different things. I have the energy stored by the magnetic field, and then also the energy stored by the electric field. And I have expressions for both of those. We saw the energy stored by the magnetic field, it's 1/2 Li squared. And then the energy stored by the by the electric field is either 1/2 CV squared or 1/2 Q squared over C. we did this back in, I don't know, remember chapter 1 or looking at capacitor. So if I want to know the maximum current, then what do I need to do? Right, so I know that the maximum energy in the magnetic field will equal the maximum energy in the electric field. Right? Because they're not going to lose energy when they go back and forth. So I know then that UB max is equal to UE max. Okay, that's 1/2 Li squared equals 1/2 Q squared over C. And then I can solve this for my current. So I can get rid of these 1/2. I squared is equal to Q squared over CL. I take the square root of both sides. But now I know C and I know L. That's my capacitance and my inductance. But I don't write offhand know Q. So how can I find Q for this circuit? This is the charge that's being stored by what? Right, the capacitor. And so how do I find the charge on the capacitor? Right, so go back to our capacitors chapter. Q is equal to CV. Right, so I can put that in. I find that it's equal to, well, I'll just put it in, substitute it in here. So this is going to be equal to the square root of C squared V squared over CL. I'll get rid of that. And it's just going to be CV squared over L. So my current then here is equal to 1.5 times 10 to the minus 6 farads. V squared, which is going to be 12 volts squared, 144, divided by just L, which is 12 millihenries. Gosh, milli, what is that? 10 to the what? Right, -3. Nano is -9, yeah. So 10 to the minus 3 henries. And that gives me my maximum current in the circuit, which is going to be 0.13 amps. 0.13 amps. When does this maximum current occur? Does it occur when the capacitor is fully charged, just half charged, or have no charge at all? When does the maximum current occur? When the capacitor is fully charged, half charged, or not charged at all? Let's do it as a clicker question. We can pull up the clickers actually. So the max current occurs when A cap is fully charged, B half charged, or C not charged at all, no charges on it at all. When does that maximum current occur? When the capacitor is fully charged, half charged, or not charged at all. Now let me ask you another question. When is the energy due to the magnetic field at its least value? What is the current when the energy due to the magnetic field is at its least value? What is I? Zero, right. When I is 0, this is 0, right? L doesn't change. nor does C. It's only I and Q that are changing. Okay? So if this is 0, when this is 0, that means this is 0. Right? So what then, if this is at its max value, what is the energy stored by the magnetic field? Is it at its max or minimum value? Is at its maximum value. So if I is really big, at its biggest value ever, that means this is going to be at its biggest value ever. Okay? Which tells you something about this value over here, the energy stored by the electric field. Alright? So, which tells you further something about the charge that's on the capacitor. So when this maximum current occurs, what is the charge on the capacitor? Right. Most of you had the wrong answer at first, but now we'll have you going around. A few more seconds. Ask your neighbor if you like. We're still about. There we go. All right. Just a few more seconds. I'll stop at 218. 218. Okay, C is the right answer. When the maximum current occurs in the circuit, remember our current goes from 0 up to some maximum value, 0 to some maximum value. And when that maximum current occurs, that's when I have the most energy stored in my inductor, in the magnetic field of this inductor. Remember, when I have a really big current, it induces a magnetic field in this inductor because that changing current, that changing current causes a magnetic field. And when that is at its maximum value, I get a 0 charge in my capacitor. Okay, so the maximum current occurs when that capacitor has no charge at all. And I get this interchange between electric field energy and magnetic field energy. Now, let's look at RLC circuits. And we'll also let me go back to this. I didn't ask this question, but I could also ask just what is the current at a particular time? Let me just show you. I'm not going to work through the numbers, but let me just show you how this works. So let's say that I just want to know what is the current at t equal, I don't know, 2.5 seconds. All right. In that case, I know that I is equal to I max times sine of omega t. And I've also found that omega is equal to the square root of 1 over Lc. Remember, this came about from that solution to that second order differential equation, that d squared root dt squared, taking the second derivative of that function. And we found that this was the solution to that function. And so if I want to know what is the current at a particular time, I know now that I max is 0.13 amps. I would say the sine of the square root of 1 over Lc, whatever that is, right? Our L is given, our C is given, times 2.5 seconds. And then that would equal to whatever our current is. We'll do some sample problems later when we look at different types of circuits, where you're just plugging in numbers here to find the current, the voltage, or the charge at a particular time. But in this case, it's really just a matter of putting in the right numbers. You'll have all these expressions on your equation sheet, by the way, the current for an LC circuit, the current for an Rlc circuit, and all that business. Okay? I'll have that out soon so you can sort of be familiarized with it. By the way, whenever we're working in this chapter, you want to be very careful, and I'll remind you of this on the test, but when you're doing these trig functions, you want to have your calculator in radian mode. And I'm pretty sure, yeah, on this next test, your calculator needs to be in radian mode for the entire test. But I'll remind you right before the test, okay, so that you don't forget. How many tests when I was in college I messed up because I didn't change my calculator over to radian mode? Did you ever do that? Yeah. What's that? You know, especially in physics, because like if you're dealing with vectors and you're dealing with degrees for the vectors, you need it in degree mode. But when you're dealing with functions like this, you have to have it in radian mode, because your omega, that angular frequency, is measured in radians per second. All right. Also, I just want to remind you, we'll see this again, but this omega is equal to 2 pi times the frequency, which is the frequency that we normally think of. But the angular frequency, instead of being 1 over seconds, is measured in radians per second. I'll show you in a little while what that means and how it applies. All right, let's look at LRC circuits. So we've done LC circuits and LR circuits, but now we're going to put them together. Haven't we done LR circuits? We did. Yeah, we saw LR circuits, where we had the decay and the growth curves. So we're going to look at damped oscillations now, where we put these two together. You're probably never going to see LRC circuits or LR circuits or any of that business again, but you could very likely see some of these mathematical tools that we're sort of touching on. Damped oscillations in Rlc circuits. So these are circuits that are going to contain what? Right, and inductors, right. So the R is for resistors, L is for inductors, and C is for capacitors. So we'll have all three. So the LC circuit, which we just did, loses no energy. The reason is because we said before, because, what's that? Right, there's a transfer of energy, but because the electric and magnetic forces are conservative, that's the reason they lose no energy, because those are field forces, they're conservative forces. But if you have a resistor, that resistor will dissipate energy. And it actually dissipates energy at a rate of P is equal to VI. We saw that before, that it dissipates that energy per unit time at a rate of our voltage times our current. All right, so we have a total stored energy in our LRC circuit. Right, we have this circuit that has an inductor, it has a resistor, and it has a capacitor. No power supply yet. We'll get into that probably next week or Friday. But I have a total stored energy. I have energy that's stored by the inductor because there's a magnetic field in the inductor, and that's going to store energy. So I have a UB. I also have energy stored by the electric field in the capacitor, and as we've already seen, this is equal to Li squared over 2 plus Q squared over 2C. So 1/2 Li squared, 1/2 Q squared over C. That's our total stored energy. Now, this is going to decrease. Energy decreases at this rate. I call it du dt, because that's the amount that the energy changes, is equal to negative I squared R. If you remember, we had P equal VI, but we also had an alternate term for this, P equal I squared R. So that's just our power from chapter 4 or 5 or whatever it was that we had. All right, so we have this total stored energy, and then we have this other term. And so I can put these two together. and I get an expression that looks like this. I get the du dt is equal to Li di dt. Excuse me, let me rewrite that. That's not a subscript. That's a plus q over c dq dt. And this is all equal to, so that's the change in the stored energy. Both of those are how our stored energy changes. That's just those two sums that I did before, but how they change. And then this is going to equal to negative I squared R. This is our rate of change of energy at any particular time. What we're doing is we're trying to get to an expression that allows us to get the charge or the current at a particular time. All right, so I can say that I is equal to dq dt, so I get L times dq dt. That's from here. I can further say that this is the second derivative, d squared q dt squared. Plus, I'm going to bring this term over here, so I get R dq dt dq dt. I'll show you why I'm writing this in just a second, but basically what I'm doing is I is equal to dq dt, and then I square it, plus 1 over cq dq dt. And this is all equal to 0. Right. So I have this expression. What can I do with this right off just to make it more simplified? There's a term that's, right, that term can go away, right? I can just divide through by dq dt, and I just get rid of it completely. So I can get rid of this, this, and this. And then I get this differential equation. Well, it's going to be a, well, let me just write it out, I'll show you. So it's L d squared q dt squared. It's not a quadratic function. It's going to be a second order differential equation. Plus R dq dt plus 1 over cq. And this is all equal to 0. So this is a second order differential equation, ordinary differential equation. And I want to find a solution for Q that will make this true. All right. Can you think of a solution for Q that might make this true? What type of function would it be? Where I have a function Q, a function that is the derivative of that function Q, and then a function that is the second derivative of that function Q, that would all add up to equal to 0. It's either a trig or an exponential function. Which do you think it is? Well, if you think about it, if it's a trigonometric function, like if this was sine, what would this be? Cosine, and then what would this be? Negative sine. So would those add up equal 0? Yeah, you'd have to do that for the cosine, and then you can work out your coefficients to make them. Right, but if it was an exponential function, say I had e to the minus x, right, then I would get a negative that would come in each time. So it is an exponential function that can make this equal to 0. And the exponential function happens to look like this. We're not going to go through sort of the method of solving it, but you will in differential equations. But it's going to be an exponential function, negative RT over 2L times the cosine of omega t plus phi. Oh, and actually, this is an omega prime. I'll show you what this is. Again, you don't try to memorize this. I'll provide this for you. but omega prime is equal to omega squared minus r over 2l squared, and omega is equal to 1 over root LC. All right, so that's going to be the charge on our capacitor at any given time. I think that we've talked about this phi. Y'all know what this is? I don't know if did we determine we did oscillations last semester? Did we do oscillations?
No, you and I said one last class.
Oh, okay. All right, that must have been taken out. But phi is called a phase constant. We're going to talk about it more, so I want to address it here just a little bit. A phase constant, and by the way, I could give you some sinusoidal functions and ask you to interpret the phase constant for these various things. We're going to get into phasors next time, and it'll be important that you understand phase constant. It's not that difficult though. So let's say that I have a function, a sine function. We'll call it sine of omega t. All right. So sine of omega t. Let's see, at t equals 0, sine is equal to what? If that omega t is equal to 0, what is sine? Is 0, right? So it's going to start right here, and then this function will oscillate back and forth at an angular frequency of omega. Okay. Now let's say that I want to write a function sine of omega t plus 90 degrees. All right. So at t equals 0, what is the value of that function? It's equal to 1. So this function is going to start here, and it's going to go through like this. All right. So this function has been shifted over by the phase constant omega, or by the phase constant phi. And in fact, this function has been shifted over by 90 degrees. You can also shift it over by 180 degrees. If I shift it over by 180 degrees, what is the sine of omega t plus 180? I'll write it down here. The sine of omega t plus 180 degrees. It's equal to 0 as well, right? But this time, it's going to look like this. I'll start down here. Right, your function will look like this. All right, so it's like the, what's that called? Like a destructive, like where if you add them up, they go to 0. It's the opposite of the other function. We'll see phase angle again, phase shift soon, because we're going to get into phasors and sort of how to use those as a mathematical tool. All right, if I were to plot the energy versus time for this function right here, where I have this this cosine function and I have this exponential function, the cosine function will make the charge do what? What does a cosine function do? Is this exciting for y'all? Do y'all like cosine functions? What does a cosine function do, y'all? Yeah, right. It oscillates, right? Yeah, it just goes back and forth between two constant values. And what does an exponential function with a negative exponent or sort of power like this do? Well, as the value t gets bigger here, what happens to that exponential function? Does it get bigger or smaller? Right here. Just looking at this function right here. Just imagine this is like e to the minus t, right? If t gets bigger, what happens to this number? It gets smaller, right? Any number to a negative exponent, where the negative exponent gets more negative, is going to get smaller. So what I get here for my charge, and actually as it turns out my energy as well, is I'll get some combination of those, u and t, where my energy starts out big and it will oscillate back and forth, but it's going to decay by that exponential curve. It's like a cosine function combined with an exponential function. You ever seen a function like that before in like your calculus class or whatever? Okay. Y'all might see it in PChem, I suspect, where you combine these sinusoidal, these oscillating functions along with these exponential decay curves. If not, you'll definitely see it in differential equations. Okay, so that's the basic outlay of that. You need to know how the energy behaves in this. Daniel? The no, it's not. It's just the current, yeah. But it's differentiating now. We're going to get into where capital I is going to be our maximum current, and little I will be our current as a function of time, right? An instantaneous current. Because now our current's changing. All along the semester, our current's always been constant for the most part. But here, we're going to have a changing current. Okay, let's do an example. Alright, so let's see. I have an RLC circuit. Again, you'll have a homework problem that'll be similar to this for more practice. Our capacitance is 1.6 microfarads, resistance is 1.5 ohms, and our inductor is 12 millihenries. And I want to know a couple of things. Well, let's see. I have it worked out. I don't have the question. Okay, when is the charge on the capacitor at half its maximum value? Alright, I know that Q is equal to big Q times e to the minus RT over 2L times the cosine of omega prime t. Let's see. Oh, I'm missing something. I didn't write something in my notes. I forget what I was asking. I'm sorry. I'm going to go on and work through it, and then we'll come back. I'm sorry. I forgot what I was asking here. But it wasn't exactly when is Q. It must have been when is the maximum Q at half the original charge. Okay. I'll come back to you on this next time, but I'm going to have it such that this cosine goes away. That means that I'm going to have my maximum charge at a certain time. So if I look at my function, it looks like this. And I want to know where along this function is Q at half its original value. You follow what I'm saying? It means that the cosine function is going to have a value of equal to 1. All right. So the way this will work out is I'll have Q e to the minus RT over 2L is equal to half of my original Q. And then you have to solve that for t. Y'all know how to solve an exponential function for a value in the exponent? Right, so you want to take the natural log. Why don't you try this on your own? I'll go ahead and set it up for you. But I have e to the minus r was 1.5 ohms, t over 2L, which is 24 times 10 to the minus 3 is equal to a half. let me know when you get t. What is the value that you get for t here? If you finish that one, go ahead and ask the question, how many oscillations occur in this time? So I'm looking for the point at one of these peaks where Q is equal to half the original charge, and I want to know how many oscillations occur in that time. Think about your angular frequency, omega. You might have the time for me?
Yeah, I don't know how to do the natural thing.
Okay.
I don't
Okay. That's fine. Let me show you. So it's not that hard. If I do a natural log over here, that gets rid of this. And I'm left with, on this side, negative 1.5 t over 24 times 10 to the minus 3. If I do a natural log over here, I just get natural log of 1/2. You're going to get a negative number for that. Did I get the point you got? What did you get?
I don't know if I checked it's
1,109. I think you're just, yeah, you just did your exponents wrong somewhere along the way. That's not right, but it's the right numbers, just the decimal place is in the wrong place. All right, so if I solve this for t, what's the natural log of 1/2, somebody? Okay, I don't know right off. Is that right? Somebody confirm that? Okay, so negative 1.5 t 24 times 10 to the minus 3. If I solve this for t, should look something like this. I'll get 0.011 seconds. That's what I got. Is that what you got? Yeah. You'll have to solve a function like that, okay? The exponential comes up in several problems, so make sure that you're able to do that. All right. Now, what about the second question? Is how many of these oscillations, if I want to know where is the charge at this peak, at its half its maximum value, how many oscillations have gone through that cosine function in order to get me to that point? All right, remember our omega, our angular frequency, is equal to 2 pi f, right? So also remember that frequency is 1 over the period, and the period is the time for one complete oscillation. So in order to find how many oscillations, I just want to say that total time, that 0.011 seconds, divided by my period. And then that'll tell me how many oscillations have gone through the cycle in this RLC circuit. So if I do that, I find, first of all, I also know that for an inductor circuit, that this omega is 1 over square root of LC. We had seen that before. That'll be on your equation sheet, but you need to know that it exists and it's there. That's my angular frequency for this LC circuit or for this LRC circuit. Though when we're looking at the cosine function, we're really just concerned with the LC portion of the circuit, because that's what causes this interchange of energies. All right, so I can take these three and put them together, and I get that the period is 2 pi over omega, which is equal to 2 pi square root of LC. And if I want to know the total number of oscillations, I just say 0.011 divided by 2 pi square root of LC, where L is 12 times 10 to the minus 3, and C is 1.6 microfarads times 10 to the minus 6 farads. And that'll give me the number of oscillations. It turns out to be about 13 oscillations. So that means if I look at my charge versus time, and our energy follows this, but also our charge follows this function. Let's see, cosine of 0 is 1, right? That means that out here at number 13, this isn't 13, but out here at number 13 is where my charge goes out to half the original charge, the 13th oscillation. All right, we're going to start on alternating current next time, and we'll look at 3 additional circuits. These are all going to be pretty simple circuits, but you'll have homework problems for each one. But they're all pretty basic circuits. We'll look at alternating current with a resistor, alternating current with an inductor, and alternating current with a capacitor. We'll also get into phasors. I don't know if you've ever used phasors in PChem, but it's possible. I'll have to ask Dr. Lowe, see if y'all use that in PChem at all. Nobody's in PChem, right? Do y'all use phasors at all? You do oscillating functions? You do that, right? Like in quantum? Are you in thermo or quantum? Is that thermal? That's thermal, okay. You haven't taken quantum yet? Okay. I'm pretty sure that y'all use that in quantum, but I'll have to talk to Dr. Lowe. All right, folks, we'll wrap up there.